and thank you everyone for coming to the seminar. So the title of my presentation is how can an emotional brain be rationally creative? I think this is a little bit different from what was in the introduction. When I looked at it yesterday, I had a little bit of surprise. So that was my emotional reaction to that title. And then I was trying to rationally justify what is the difference, what is the similarity between these two. So when you look at this title, usually we're going to ask a few questions. The first question is like, what is being creative? Then it comes to what is a rational brain? So what is an emotional brain? And which brain contributes to creativity the most? And how do two brains work together to bring about creativity? So those are the questions actually we have been trying to answer for design community for the last half century. And out of this kind of exploration, in myself over for the last 3 decades, I've been trying to develop a new kind of a design science to address these kind of questions. So my time at back to UC, it has established a very good important milestone for this research. So my seminar will be roughly divided into 3 major sections. So the first part, I'm going to briefly introduce the foundation of this my research, and then I'm going to give some review of our experiment research for neurocognitive investigation into design creativity. Finally, I'm going to introduce a few projects we did with the industry by applying the research results we have. So now, first let's come to the design science part. A very fundamental assumption behind our research is our creativity is very closely related to mental stress. I understand that when we see mental stress in health institutes, it's kind of people don't like it. When I remember a few years back, I talked to Dr. Kwan about mental stress. He said this is a very negative thing to describe people. But engineering, like we take it as a neutral description. So we have been going with it for many years. So what mental stress and the creativity, what is the relationships? Basically, we all have this experience. If our mental stress is too high or too low, we're not going to be very creative. So it has to be, we have to have some stress, but we cannot have too much. This is our basic observation. And this was adapted from Yerkes-Dodson law. They studied mouse for their stress and performance relationships. Then the question comes to what is mental stress? Like, and how are we going to quantify, what can we quantify mental stress and how to quantify mental stress? When we talk about the stress, the first thing it reminds me because as engineering background, from physics, we learned our pressure is the force over area. That is what we learned from physics. When we come to human being, so our mental stress, or what is our stress? Usually it depends on how much workload we have and what is the capacity we have. Like for some people, something might be very stressful, but for some other people, it's a piece of cake. So it depends on 2 things. Firstly, it's the workload. Secondly, it is the capacity, the mental capacity. So with this analogy in mind, so we kind of got a very qualitative formula to describe mental stress. So we define mental stress as a kind of a ratio between a perceived workload and our mental capacity. So mental capacity is 3 components. The first one is how much knowledge we have and how much experience we have. Second one, by skills, we mean the way of thinking, our methodology to solve problems. So those are the basic skills. And then we have emotion, affect. So affect, as we can see, we assume that it is something from 0 to 1. Like in this formula, as we can see, if our affect is very bad, if it goes to 0, no matter how capable we are, how much experience we have, how much knowledge we have, how skillful we are, our stress is going to be huge. So that is the interaction between our emotion and our rationality. The first part, knowledge and the skills, are our rational part, our rational thinking. So these two parts working together will constitute our mental capacity. So with this kind of mental capacity, then we are going to take our external workload and trying to solve the problems we see every day. I put perceived there because the workload we see may not be the real workload. It all depends on our knowledge and skill, our experience, and our emotion. Sometimes like we tend to use our experience to perceive our workloads. We use our emotion to perceive the workload. Therefore, we call it perceived workload. That is why sometimes if we can solve our emotional problems, if we can overcome our fixation, and then we can get a very clear workload, and we can make it working better for us. Apart from that, we have another function called affect and stress as a relationship. That function is kind of our stress coping mechanism. So some people, no matter how much stress they have, they will always remain cool. So their affect peak remains to be a very large number, close to 1. But some other people, when there's a little bit of uncertainty, then their emotions going down very fast, come to close to 0, and then they become very stressful. And no matter how much knowledge they have and how skillful they are, they can't do it. So that is kind of a qualitative explanation of what we have made to look at the rational part and our emotional part, how they work together to impact our decision-making abilities and impact our creativity. With this as a foundation, we have built up 2 postulates to study design creativity. The first one we see design reasoning follows recursive logic, which is nonlinear dynamics. I believe very few people from here will understand what it means. So in a very plain language, it says who we are will determine what we are going to do. And in turn, what we are going to do is going to change who we are. This is the meaning of this postulate. So this is, I kind of observed this phenomena back in 1980s when I was doing my master's. So in 1991, I formulated this phenomena into this logic called recursive logic to describe this very common phenomenon in our daily life. And then the second, so this one, basically it deals with the relationship between our workload and our knowledge and the skills. Because our knowledge and the skills kind of define like rationally who we are, so then determines how we are going to rationally solve a problem. So the second one, of course, this design creativity is related to our designer's mental stress through an inverse U-shaped curve. And this one is dealing with perception, emotion, and the stress part. Those 2 things together formulate the very foundation of my research over the last 3 decades. So over the last 3 decades, by working on these 2 postulates, and we have managed to kind of have developed a new kind of a science. I call it design science. In this science, we have 4 parts. The first part, I call it the object of study. So it studies the reasoning part and emotion part of a human being. So it's kind of a decision-making process. What are we going to study? The second 2 parts is a hypothesis. I call it postulate 1, postulate 2. This is a foundation to study the relationships between in the components in the object of study. Then this third part is the mathematical part. So how are we going to represent the each and every relationship and the components in this object of study? And so the number 4 is an experiment, the environment we developed, trying to validate what we did here and try to quantify some parts of this qualitative model. So for each one of them, approximately it took me 10 years to do one of each one of them. So today we are going to mostly focus on the fourth part, the experimental part. So the other 3 parts we are going to skip. So we're going to focus on the neurocognitive experimental research, this part. So this is the experimental environment we have. Basically, we have 2 rooms. Here you saw is the first room called the experimental room. We have control room in the other side of this separator here. So as you can see here, we have a EEG device. You see EEG, we have a skin conductance. We have 2 belts inside. One is for heart rate, another one is for respiration. We have this is eye tracking, and we also have video cameras to look at from different angles. And then we have a screen recorder to record what's going on in the screen. So that once we get all the data, when we are either doing creative design or doing other activities, then we can analyze them together to understand what is going on in our mind and in our emotion. So I'll give one example to show how we did this kind of experiment, how it looks like. Like the one experiment we did is giving a subject, give a participant a design problem. It's a design a house that can fly easily from one location to another. Just the one sentence. We give this one to a subject, then the subject is going to start to design. There's no time limit. Some people will take half an hour, some other people take 2 hours. We had one subject, he took like 5 hours, 4 hours during which he had to take a break to do this design. So this is I'm going to show how this experiment looks like. That was me. So this is the screen monitor that shows my writing on the tablet. And this is the EEG wave. We had another signals like HRV, skin conductance, or respiration is not showing here. Other videos are not showing here. And the last one actually is the results we analyzed after we finished the experiments that shows how my brain like scope map changes throughout the design process. So in doing this, as you can see from here, we have all kinds of data. The first one is text. Free text is even handwriting text. So we have a text message. We have a brain wave. This is kind of neural signal. We also have a physiological signal, like the heart rates. We have skin conductance, all those signal. We have a video. We have a facial expression. We have eye tracking. We have all kinds of data here. So in the experiment analysis, we need to deal with this all kinds of data, and then we need to find the correlation between them and to find out the underlying mechanism of the design creativity through the analysis of this data. So those are the summary of this data. And so in our research, we have adopted a lot of algorithms from the literature, and which we have to do because, as you can see, the range is so broad, it's impossible for us to do everything by ourselves. And then we had focused on 2 research parts to develop our own in-house algorithm. The first one is for the design text analysis. This one, as you can see, when somebody has finished a half an hour or 1 hour, 2 hour experiment, there are lots of text. We need to analyze what is behind the text. It's pretty much like when in health institute, when you did a questionnaire interview, so you have to do a narrative analysis to understand what's going on there. So we also do trying to find out scenarios and trying to understand, to categorize the text, to understand the meaning of text, to find the cause-effect relationships. This is the text analysis. So in this one, I developed a proposed model called a recursive object model, this one actually is echo the recursive logic I proposed in 1991. So it was after 16 years that finally I found a way to represent the contents in the logic. So this one is the purpose is trying to derive meaning from free text, try to understand the meaning of a free text, not by machine learning, but by rules, by rule-based analysis. So based on this ROM diagram and model we proposed, and then we developed an algorithm to ask questions. So the computer can automatically ask the right questions based on a text that is being given to the computer. So we developed this algorithm in 2008. Question asking is a very important thing we do as a human being. Right now, our computer can only answer questions. So like, asking questions is still a privilege for expert asking the right questions. Even for our students, sometimes it's very difficult to ask the right questions. How can the computer do that? So we have this algorithm to do that. Using this algorithm, we can design questionnaires. We can design our research. We can design our proposal. Do many things. So using those two, plus the recursive logic we proposed earlier, we developed a design methodology called the environment-based design. So this methodology is help the people to design any new products. No matter it's a software, it's a computer algorithm, it is a research proposal, it is a drug, or it is a building, so we can all follow the same procedure to do it. The purpose is to help people without much experience to do it. So that's we can, for expert, it can avoid the fixation. For novice designers, it can help you to gain the knowledge step by step to work on the new field. That is why when I was introduced, as you have seen that my background was from my PhD degree was from mechanical engineering from Calgary. My undergraduate was from civil engineering, from Nanner University back in China. So changing from the engineering field to this kind of neuroscience field involves a huge amount of work. So that is this design methodology that has helped me to make this change. And also my change has come back to help the development of this methodology. As we said, what is recursive logic? Who we are going to determine what we are going to do, and what we are going to do is going to change who we are. So another in-house tool we developed is called the task-based EEG analysis, the tEEG framework. I'm going to give a very brief introduction next few slides. Firstly, I'm going to give a brief introduction. What is a recursive object model? So in this model, we define two kinds of objects, simple objects and compound objects. Like in natural language, every word is a simple object. Every phrase, every sentence, every text is a compound object. Article is a compound object. An email is a compound object. So that we have two kinds of objects. And then we have three kinds of relationships. The first one is constraint. What is a constraint? Usually it's adjective to a noun is a constraint relationship. Adverb to a verb. And then we have connection. And then we also have a predicate, like there's things that a verb is a predicate. So we have three kinds of relationship. This is a very simple model. This model, I call it a recursive object model. And recently I found out actually a very famous linguist, Noam Chomsky, he has also been trying to develop a kind of a simple recursive model for language. But he has not able to find out the minimum component yet. So we have right now this is kind of something very hot in natural language processing. I give one example. What does it do? So I give this sentence, like the experiment we did, design a vacation house that can easily fly from one location to another location. If we draw this diagram, we can see here that this is the wrong model of this sentence. Right away from this model, we see fly is the center of this whole sentence. And the center topic of this one is the house fly. So imagine if we have an email from a patient, like a complaint from a patient. If we draw this kind of a diagram for that email, we are going to see what is the key message that the patient was trying to deliver. What is the context of the message about? So it's kind of very useful to do that. With this kind of analysis, then we put thousands of complaints together. We are going to be able to do a machine learning. So this kind of help us to do automatic annotation instead of a manual annotation in medical field. So based on that diagram, and then the computer will be able to ask questions. Usually for human being, I did experiments for this design. Over 95% of students or people, when I ask this question, they are going to start with a house. Ask the first question, what is a house? They're going to design the house. But with the computer, the first question, what is a vacation? What is the location? So we have to answer these two questions first before we go to the house. So those are questions that were generated by computer. So with these questions, there we can find the answers either from our memory or from textbook or from Google, from anywhere, from experts. We can find the answers to those questions. So then we put them back into this diagram. So this becomes more and more complex. Then from here, we can do more analysis until we finish the design. So throughout the entire design process, we have this one underlying the whole process and help us to deal with the meaning of the design, to help us to understand where we are and how we are going to proceed. This is the first thing we develop within our lab. The second thing is the tEEG framework. As we all know, like from medicine, from medical school, I think when we do a lot of experiments, we know that it's very important to every and each experiment to be repeatable, reproducible. Therefore, we have to control the experiments. We have to structure the experiment so that the data is like every control variable are controlled. So we only deal with independent variables and dependent variables, so that we can get statistically significant results. That is what we do in biology and in medicine. However, when we do deal with ecological valid experiment or real-time experiments, sometimes when we do decision making, we do those kind of things like creativity. So these things are not very controlled. We cannot control many environmental variables. So it is open-ended, it's free, it's flexible, it's less controllable, unstructured. Then many results are surprising solutions. So how can we do experiments for this one? How can we do meaningful experiments for this kind of real-life problems? That was the challenge we had been faced for many years. So that was also motivation for us to find a novel approach to deal with this kind of issue. So we proposed a loosely controlled experiment. We'll call it task-oriented or task-related EEG analysis to do this one. What we did is that in the experiment part, we try not to do unnecessary control. So if we have to leave it free, we leave it free. if we had to have that flexibility, we give the flexibility. And then what we're trying to do to work on, we're going to work on the final data and then try to find the pattern from unstructured data. So we try to find the hidden stimuli and the response relationships. Therefore, we can structure the unstructured data and find the patterns behind them. That was what we are trying to do here. As come to EEG analysis, we employed an approach called the microstate analysis. The basic principle behind it is a clustering algorithm. So it will divide our brain signals into like a milliseconds. Then they are going to do clustering analysis, find clusters. Then they will merge some clusters together. Like, then from there, we get many like micro level stimuli and response pair data. So from there, we are able to do machine learning, to do regression, to do data analysis. That was the basic idea behind it. This is the framework we have. So in the first step, we do data collection under a relatively free and open-ended, flexible, uncontrolled, less controlled experiment environments. Once we have that, we do data filtering as before. Then we do data segmentation, use clustering algorithms based on different kinds of data. So once we get the segmentation, then we group them. We're going to do different hypothesis tests. So for the whole, we get the real-time, real-life data collection. Then we are going to dig in. We divide them into smaller chunks. So then we find the hypothesis for each small clusters. So once we get the clusters, then we are able to identify artifacts. We can do feature extraction. We can do classification analysis. We can do regression. We can do many other things. That's what we have been doing in traditional scientific research. This was a second contribution we made in this analysis. Others are just follow the traditional methods. Using these things, like our experiment design have evolved through 4 stages. But the driving forces for these 4 stages are 3. The first one, we are always trying to improve the accuracy and the convenience of devices for data collection. For example, when we have to do brain signal, do EEG analysis, sometimes it took half an hour, even longer to put the electrodes on the subject's head. So we have to try to make it more convenient, but we make it more accurate. Second thing we need to consider is the levels of control we have to add to the activity to experiment. Even though we are quite flexible, we still want to have to do some feasible control so that the data can be more accurate. And then the third one is we have to develop new data analysis techniques so that we are able to structure the unstructured data. So that is a balance between the algorithm, the robustness of the algorithm, and the flexibility of the experiment that we can have. So if we can have a very accurate, powerful algorithm, we can give more freedom and the flexibility to our experiment design. Other vice versa. I think that is the motivation behind it. And I will briefly walk through our experiment evolution. The first stage, like what was in 2007, 2008, we tried to test if the EEG can be used to study human creativity, design creativity. So we did a pilot study. We use a very simple EEG system. It's 8-channel system, and then we did the study. And after that, we learned some lessons and we proved that it's feasible to do it. Then we move to a second stage. We secure some funding. We are able to increase our device from 8 channels to 14 channels. And then we are trying to test the postulate, the second postulate, the relationships between our creativity and our mental stress. So we started to do that, and then that was a flying house experiment. And since it's very unstructured, our success was limited. Then the third stage, we went back a little bit more structured design tasks. We used 6 design tasks and put them together, trying to simulate the complex design. And then here we get a new EEG device, which is 64 channels. And we get a very good data synchronization in tool. And the data is more structured, even though we still have a lot of flexibility. So with these 2 things, we are able to produce a lot of meaningful results. After that, then finally, after about 10 years, and then finally we moved to creativity research. We did experiment on creativity, and we got some interesting results from there too. So I will go very fast for this one. This is the brief introduction. The first stage, as we said, the objective is to test if EEG signals can be used to distinguish design activities. And then from there, our preliminary experiments, we found found for problem analysis, solution evaluation, and the solution expression. We have 3 activities there. So we found out subjects expend most of our mental efforts in reflection and judging during problem analysis and the solution evaluation. And while in solution generation, the visual thinking is dominant. That is a very interesting finding, and it confirms experiments like people did back in 1994, not using like the neuroscience approach, using traditional protocol analysis methods. They found this way. We found once we get this confirmation, we are encouraged, and we kind of see there's a feasibility there to apply EEG to study creativity. I think we are the one of the very first groups in this area to do it. And right now, this community is growing very fast. We get quite more and more people are joining, and we also get people from neuroscience starting to do this research. And in a couple of months, we are going to hosting a workshop called Design Science meets Neuroscience. We have managed to invite some people from pure neuroscience, and we get some people from design science. We are going to talk to each other to look at each other's research and see what we can do together to build up some common ground for these 2 communities. But from here, we learned some lessons as well, and then based on the lessons we learned, we purchased a new EEG cap. As you could see from the figure, there's no EEG cap. And then we increased the EEG channel to 14, and then we divided the room into control room and experiment room. And then we also changed the coding method, because before we had 3 categorization. And now we are, because we ask a human to do the coding, and they found huge discrepancies between the 2 people to do that. And we are trying to introduce the methodology we developed ourselves and to change the coding method. So for the second stage, then objective is to validate this our postulate to invert the U curve. That was, we didn't know that at that time. This was actually a very challenging task. Even in psychology, people have been trying to validate this one. No one has been very successful in psychology. But since we were very new in psychology, we didn't think we are psychology people, we are engineers. So we even didn't check how they did. We took this program, but we got some interesting results. We did the experiment. This is a very free experiment. We divided the experiment into first half and the second half. With the first half, it is more, people focus more on solution generation. The second half, they spend more time to evaluate the solution. Again, we found out that in the first half, the visual spatial processing was more active. This was consistent with our pilot experiment we did. And the The second half, on the other hand, we found that like they experience more stress compared to the beginning of design process, because in the beginning we only had one sentence. They didn't have much information to start with, and that problem is quite a familiar problem to people. They see design a house that can fly. They think about balloon and airplane, so it wasn't very stressful. But after they have done some, spend some time to do experiments, more information is received, then they have to deal with the information, so they get more stressful. That but we were not able to validate that inverse the U curve, and but we did get some interesting observation from there. And this became the first journal paper we were able to publish. Like we started this research in 2004, but after 10 years, we finally were able to publish these results in a very good journal in our area. So from a second experiment, again, we learned some lessons, and so our decision is to purchase a new EEG set to remove the environment noise. And we also purchased the captive system to help us to synchronize our data. And we have changed our design task, make it more structured. So this was the third kind of experiment we did. So now we added a subjective measure to assess workloads, knowledge, and skill, because before there's no ground truth, no baseline to see when people are stressful. So now we use a NASA task alert index as a baseline to see how it will work. And from there, and then we found out that subjects actually continue to feel stressed even after the tests were over, and also that the stress recovery is always delayed. So what we learned from here, subjective rating of mental stress is not very sensitive to small variation, and the subjective rating may be affected by stress and effort. So designer stress will be induced during the design process, will continue to last even after the design is completed. What we learn from this one is that when we do qualitative research, we ask how people feel and ask their opinion. All those things we kind of see, those opinions are often biased by their experience, biased by their stress, their perception. So this helped us in, later I'm going to give a industrial project that we did. We learned from here. I think this experience helped us to design our questionnaire in that project. So that's the one, what we did is creativity research, and then we give a very simple stimuli to the subject and ask the subject first to write down what they intuitively saw when they saw this symbol, and then draw what they saw. That is we call it non-creative research. It's intuitive design. The second step is that we ask them to draw something that is radically different from what they intuitively saw and from what they have seen. We try to invoke creativity. So we did many experiments, and we get interesting results. Recently, we get very good results, and those results are under review, it's revised and it's under review for scientific reports and other journal. So those are basically our experiments we did. I'm moving to a few applications we have done based on those theoretical research we did. So over the last, since I joined Concordia, we have collaborated with many companies, like aerospace companies like Bombardier, Pratt & Whitney, Bell Helicopter, and Royal-Ross, those aerospace companies. And we are also working with CAE is another aerospace company. We're also working with the city of Edmonton for their policy making Like how do they make like the quality? How do they have a policy to improve their service? So we did a quality manual for them, and we also work with a company a construction company in Edmonton, SMA, to help them to develop their workflow, like to improve their workflow. Suncor, we worked with them for their key performance indicators improvements, like for a project with them. And with the ProShip is a company doing in human resources. They're trying to match musicians with cruise ships. Before they did it manually, and then we designed the algorithm to help them to do this automatic match. Yeah, this is the principle is pretty much like online dating and many other things. And then Novatech is a company is doing medical device design. So we designed some medical testing kit for them. And they are still, it's still two, we did the two products for them. They're still their key products for the company. Minicut International is a machine tool company. And then Autodesk, I think most of you know it is a computer-aided design company. So we did they kind of adopted our natural language processing algorithm and to their system, and then they develop a patent out of this algorithm. Eventually, they want to have the whole thing, but because they want to have the IP of the whole thing, so we, as a researcher, we cannot do that. So then I went ahead to develop themselves. Those are the few key projects companies we collaborated with. So if I categorize the projects we did, we can have 5 categories. The first one is algorithm design, and there some are like the geometric modeling, image processing algorithms, and some are natural language processing algorithms. So we use our design methodology to design those algorithms for which we are not an expert. So those algorithms work very well, and sometimes it's even it's like for quite a few, it's better than the most widely used algorithm in the field. The second one is a product design for medical companies. The third one is a process design. We developed like some procedure for aerospace company in Montreal to secure collaboration. There's a privacy, security, and collaboration. How can they put it together? We did quality management for City of Edmonton. We did a risk analysis for the construction company in Edmonton. And the human resource management, we did this for this musician cruise liner matching. We also did for aerospace company for their key performance indicators for the human resource management for engineers. And lastly, in recent years, we have been working on teaching and learning design. And those are 3 things I can I'll give a little bit more introduction about them, because there are 3 major projects we did. The first one is the program by Aerospace Design Chair program we did for the last 5 years. So as you know, any education program is trying to equip students with the knowledge, skills, and the attributes that is necessary for their profession. So how are you going to do that? How can we equip them with this proper knowledge, skills, and attributes? That is the goal of education. So we used that formula we had, and then we designed the entire program. So we take the teaching materials as a workload. So what kind of materials we have to teach students? Traditional materials and the materials from the industry. Then we analyze the mental stress the students might have in learning each one of them. Then we try to find out the novel approaches to teach the students to learn and teach students to do it properly. So this by doing this, we have been trying to reform the undergraduate aerospace program so that when the students graduate, they can merge themselves into industry in a much shorter time. Okay, in the past, it took industry 10 years for one new graduate to become a system engineer. But now we try to shorten the time, reduce it to within 5 years. I think with this new kind of methodology, we are seeing some preliminary results. The second one is organizational lean change management for aerospace company, because the company has been trying to change. Their working philosophy has been trying to change, but they get a lot of resistance from their employees. Then they invested a huge amount of money, asked a team of researchers from the university to help them to do this change. My task is as two parts. The first one is the change management. The second one is the human resource management. I used it again for this formula to model their organization. So model their capability, model their knowledge, their skills, and their emotion, and try to find out their workload. Particularly, we paid a huge amount of attention to their perception. So, and then in this process, we designed a questionnaire, like a very easy questionnaire for them to answer, and then we get a very accurate measurement of this organization's capability in status. So their managers in the beginning, they are not very willing to spend much time with us, but once we get these results, they are very impressed, because they told us that is exactly what their organization was, and that was exactly the problem they had. And so they eventually they went with us and adopted our results into their change management framework. So this change can be from there. We divide them into these 4 parts: perceived workload, organizational knowledge, organizational skills, and the organizational effect. So this comes to the activity learning, the training, learning, and the positive emotion. This is the culture part, and the correct perception. This comes to the methodology part. So we give them a very simple training, so that they were able to solve the problem much faster and much easier. So the third project we are still doing is adaptive pilot training. So this was the experiment we have been doing. We did back in February this year. So that was a simulator, flight simulator that was installed at Concordia. So the subject is sitting there to try to control the simulator on different kind of situations. The person sitting on the right-hand side is the instructor from the company, trying to teach the subject how to drive an airplane, how to fly an airplane. Then the subject was monitored in their EEG waves, in their skin conductor, heart rates, everything. And once we get the data, and we are trying to do an analysis. That was we are still doing it, but this experiment stopped because of this COVID-19. So we are trying to restart experiment next year, next summer. Hopefully, we can start to do it, to do the experiment. So this one, what we are trying to do is that in the past, it's like a professor teaching in the classroom. So professor will observe how the students react to their affective and cognitive reactions. We try to estimate that what is the status. Then we adjust our pace of teaching. And the same thing happened to pilot training in the past. So now what we're trying to do, we are trying to bridge this gap so that we can have the complete and closed feedback loop. And the machine will tell this instructor what is the stress level at this stage, what is the affective state of the pilot, so that instructor can do it more efficiently and effectively. So those are 3 applications we had. Again, we come back to this is the general design science framework we established over last 3 decades. So then there's 4 components, but today I mainly focused on the last one. The first 3 is kind of the foundation for the last one. And last one we also validated the first 3. So this concludes my my presentation. Thank you for your attention.
For more information on who we are and what we offer, visit our website at coming.ucalgary.ca/CHI. If you are interested in our services, collaborating with our team, or have any other inquiries, contact us via email at chi@ucalgary.ca.